biological standpoint. So that'll be a fun one. And then we still have one more mass event, and it's a very fun family-friendly event. Bring your family, bring your children. This is the Science Wizard. He is awesome. I've seen him perform before. We had him last year, and the event was massive. It was really, really, really cool. So please make sure you go to the Science Wizard on April 11th. And then, of course, we have our Great Valley Museum with the hours up there. And then we have other events that happen at our museum. And I won't take up any more time. I'll leave the floor to Alex, our speaker today. And let's switch this over. And then we'll leave it to you.
Awesome.
All right.
Thanks, Georgia. Oh. Oh.
One of the screens today. One went down.
That's all right, I guess. We'll just look over here.
We should be able to get that up.
Is there?
Oh, what happened? Tried to start early. Right? Oh, no. Now we got two of them. Okay.
Oh, okay. All right.
Little Reese.
I'll start. So thanks everyone for being here. It's exciting to see a lot of people. I'm Alex Martin-Ginnold. I'm a biomedical engineer. I work in medical diagnostic devices. So right now I work at a company that's making a medical robot that can allow doctors to more accurately sample and diagnose lung cancer. And earlier in my career, I worked in a field called molecular diagnostics that's basically telling if you're sick from samples like blood and saliva and other samples, telling if you're sick. Oh, yeah, I'll project. But I'm not just going to talk about my own experience today. I want to talk about biomedical engineering kind of as a field to give you an idea of all of the things you can do with it. It's a really broad field. So I've chosen several recent research results, 7 from the last 5 months. So really new research in the academic realm that kind of runs the gamut across all the different areas of biomedical engineering you could focus on. So I mentioned that it's a really broad field. So I'm going to go through a few examples. Most of these are kind of commercial biomedically engineered devices. And I'll just kind of run through the picture. So in the top left is a surgical robot. That's over the last 20 years, they've developed this technology that lets surgeons operate remotely. So in this photo, you can see the surgeon kind of sitting away from the patient. The robot has all these arms coming down to perform the surgery. This lets them do surgery much more accurately. So imagine if your hands never shook, or you could move really, really precisely. Another cool aspect of this is that you can perform the surgery across the room or across the country or across the world. So you can access the best doctors without having to travel to them and get as many people as possible access to great care. In the middle there is a COVID antigen test. We're all much more familiar with that probably than we ever wanted to be. But that's a big part of biomedical engineering is medical diagnostics. So being able to tell if you're sick or not. In the far right is a total knee replacement, and joint replacements in general are able to really improve people's quality of life, especially for conditions like arthritis. So in arthritis, the cartilage that kind of cushions and lubricates the 2 bones in a joint wears down, and it can cause a lot of pain. So we've developed replacements that are made of metal and plastic that can alleviate a lot of those symptoms. Moving to the bottom row from the right is a prosthetic user using a prosthetic hand. That hand is more like a biological hand, but prosthetic devices kind of range from very similar to biological, mimicking the human hand, to more simple devices. And the latest advancements are in how we can actually control, when you don't have all of the muscles of your arm, how you can control all of the movement in those, really fine motor skills in the hand. In the middle there is a diagram of CRISPR. So this is more at the micro level. CRISPR is a pretty recently developed technology that allows you to fairly easily edit genetic code. So that can be to change the function of molecules or potentially to cure genetic diseases. The last example here is an exoskeleton for the lower limb. So that's something that has motors that a person can wear, in this case, a person with total paralysis of the lower limb, so full spinal cord injury, that allows them to walk on 2 feet. Most of the success in that field, I'll talk a little bit more about it later, but most of the successful products in that field have been directed at people with total spinal cord injury. There's a lot more people out there that might want some assistance walking. So I'll talk more about that later. So kind of continuing the theme of the breadth of biomedical engineering, I think it can be broken down into several components. I kind of chose these. Some of them align with like high school subjects. Some of them are a little more vague, but I'm going to go through one by one. So mechanics is just like building things. Like if you like playing with Legos, working on cars, fixing electronics, that's the type of thing that would draw you in, I think. Physics, chemistry, biology, they're all the fundamental sciences that deal with how the world around us works and how everything interacts with everything else at different levels of complexity. So for physics, we're dealing with fundamental forces like gravity. In biology, we're dealing with the interactions between cells, organs, and whole organisms. And chemistry kind of hovers in between. It bridges the gap and deals with, all of these things build on each other, but you can kind of be an expert in one without having all of the knowledge of all of the other ones. Math is essential as an engineer, but it's really just a tool. It's useful in that it lets you predict how things are going to work before actually having to make something. So an example is like you could build 1,000 cars using guesswork before you end up with a good one. You do a little bit of math and you build one, and then it works. So really essential skill, and not daunting, not too daunting, hopefully. And computer science, also kind of a tool. Computers are really good at some things, not so good at others. And also some things that we have to do aren't really that fun. They're really hard or really repetitive. So sometimes computers can really help speed things up or just make your life easier. So I think of computer science as like, if you're interested in computers, you can make yours or a lot of other people's lives much easier using them. That little chart in the middle is where I fall. So I don't know if anybody played Pokemon, but this is like the Pokemon beauty contest chart of me as a biomedical engineer. So lots of math, computer science, and mechanics. Enough chemistry, biology, and physics to get by, but it's really not my expertise. And I'm going to encourage all of you to think about that. Actually, if you go to slido.com on your phones and type in that number, I'm interested in getting a survey of where all of you guys fall. So I'll give you some time. I have a little more to talk about on this slide. So if you want to do that, I'm asking you to rank your top 3 favorite components of biomedical engineering. That can be favorite, like you're interested in it. It doesn't have to be what you're already good at. And this chart will show up again throughout the presentation. With each of the projects I present, I kind of tried to rank it as, where does this project fall in the different components of biomedical engineering? And we'll see where the class falls relative to each of these, or not class, group, falls relative to each of these components. So while you guys work on that, I'm going to talk about the essential skills of any biomedical engineer, right? Maybe your beauty contest chart looks different from this, but no matter what you do, you need these essential skills. So some knowledge of medicine and public health, right? You're building things, but you need to know what to build, what disease conditions are affecting the most people or affecting people the most seriously, and what is a priority, as a society for us to deal with. Ethics. Is it okay? Is what we're doing okay? Are we going to hurt people? Is the cost-benefit analysis, what does it look like? Is it too risky to do this thing that we're thinking of doing that maybe could help some people? And then communication. You can be an expert at every other thing on this slide, but nobody will know if you can't communicate it, right? Your ideas are only as good as your ability to share them with other people. So let's see. We'll see if the technology thing works. And is anybody on to Slido? We'll see as the responses come in. Okay. Lots of biology. Biology, chemistry. Biology and chemistry definitely leading, I think. And math. Good for you guys. I'm surprised by the math thing, but I like math too, so I'm not upset. Okay, I'm gonna just, for the sake of time, move on, but I think all the biology and chemistry people in the room will be pretty satisfied with this presentation. There's a lot of stuff that focuses specifically on those two topics. So moving on, the format of the presentation is I'm gonna have sort of a slide that focuses on that public health medicine thing. Why are we doing this? And then a slide that goes through the research. So the first thing I'm gonna focus on is hepatitis C. Hepatitis C affects 50 to 60 million people around the world have hepatitis C. It causes liver damage, leading to liver failure and cancer. And around 1 million people each year die from hepatitis B and C combined. It's the statistic I could find. The good news is that 95% of cases can be cured using direct-acting antivirals. The bad news is that access to actually testing for HCV is really low. Only 20% of cases are diagnosed. This is partly because the current testing method is 2 steps. The first is pretty easy, pretty cheap, but that first test only tells you that you need to go get another test. It's much more expensive and harder to find. So a lot of people drop off after that first step. So there's effort now to creating devices that can be one step, low cost, and brought to where people are, right? In rural areas where you maybe don't have a big hospital that you can go to get this fancy test. And the earlier you can catch the disease, the earlier you can cure it, and the less permanent damage there is to the liver, and less risk of negative effects. So that's exactly what this group did. This one has a really wide range in those biomedical engineering components. So on the mechanics side, they needed to build something that took a blood sample, automatically did all the things that you see somebody in a biology lab doing, moving fluid from test tube to test tube and mixing things. So they made a physical device that has a bunch of fluid channels where the fluid can flow, and they can put all of the different reagents in it. This is a field called microfluidics. And loaded that up with all the biology that needed to happen, and created some software to automate that. So all they have to do is create the build the thing, put in the sample, and then it spits out a result. So there's your mechanics. Chemistry and biology, this one's pretty cool. So this one relies on chemistry for our detection. Biology you have to know because you need to know how HCV is going to work in the body. So viruses and HCV included release antigens into the bloodstream that are kind of like their signature, right? And we have molecules in our own body that will attach to those things. So we can kind of grab onto that signature. And what they did here is in their little channels, they put a bunch of those little things that are going to grab onto the HCV antigens. So that's step one. So now you've captured all these HCV things. You can wash away all the rest of the stuff. Everything that you don't want to see, you get rid of it. But the HCV will stay. The next step is you put in some platinum beads. Platinum, just the metal platinum. Those platinum beads have more little HCV grabbers attached. So you wash that through, and now you have this whole channel. If there's HCV, it's filled with platinum beads. If there's no HCV, there's no platinum beads. This is where the chemistry comes in. Platinum catalyzes a reaction in the presence of hydrogen peroxide, H2O2, that decomposes that into oxygen gas and water. Basically, if there's HCV, you're going to start seeing bubbles. And that's what that top picture shows. On the left, you have your channel full of bubbles with an HCV positive specimen. On the right, channel with no bubbles, that's HCV negative. So you end up with all of these different components, right? You have to think about kind of everything around this little chart. But to get to a really simple process, something that when they tested it, they gave instructions to untrained users and expert users, right? People with a lot of academic background and people with none. And they got the same results. The analysis side, right? It's not just looking at bubbles. It's using a camera to look at the bubbles and a computer to determine whether it's positive or not. This is to get around variation, right? Like the bubbles I see might not be the same as the bubbles you all see. So using the camera gives a more accurate result. And they used an AI model to do that. So they gave, in general, their AI comes up a couple of times. So all of the AI models that they use in here work this, or in all of the slides I present, work the same way. They collect a bunch of data that they know what's happening, right? A bunch of pictures where they know it's positive for HCV, a bunch of pictures where they know it's negative for HCV. They throw it into a computer. The computer, through a lot of math, computer science stuff, looks at all those pictures and figures out what essential things about those images mean HCV positive or HCV negative. You give it enough training and practice, and eventually you can give it a picture that it's never seen before, and it'll tell you that's HCV positive or that's HCV negative. That's like the very high level overview of AI. That this isn't like ChatGPT AI, like generative AI, different type of AI. But that's how it works in all of these slides. So slide 1, going a little bit slower than I expected. Next one I want to talk about is prosthetics. There's around 35 million people around the world that use a prosthetic. Specifically, I'm going to talk about upper limb prosthetics. One of the big frustrations for prosthetic users is learning how to use the prosthetic, training with it. It's not very intuitive, and you don't have any, innervation. You don't have any feeling in your prosthetic limb, so it can be difficult to coordinate. And even more difficult is, one, finding people to test out all your new methods, right? Let's say you have a great idea for how you could improve prosthetic users' lives. You still need to get people to sign on to probably tedious, maybe difficult or sometimes painful trial if you have to do a bunch of testing with your prosthetic. So there's efforts to improve training and efforts to make prosthetics a little bit smarter. So all that coordination, maybe you can try to do something and the prosthetic can help you out a little bit. So this next research group focused on those two things. The first thing they did was implement a virtual reality training environment. So one, you don't have to change your prosthetic or do a bunch of big operations or big, you don't have to do a bunch to change how the prosthetic works, right? You just change some code, and then the virtual prosthetic that only appears. So that arm there, sorry for the low res photo. This is what the paper had, but that arm there is just existing in the virtual world, and somebody can see it, if they're wearing their little VR goggles, they can see it interacting. To change how that works, it's just a few lines of code. The other benefit of this is that if you want to try new control methods, so new ways to tell that arm how to work, you don't need to enlist people that are missing an arm to help you, right? That's, of course, in later stages, the best case. But if you're just experimenting around, if you're working in this VR environment, you can just virtually control the arm, even if you have a fully intact limb. So that's the benefit of the virtual versus real world experimentation. What they did was implement a really classic test for dexterity for people with prosthetic, which is just moving blocks from one side of a box to another over a wall. How quickly they can do this gives kind of a grade on how dexterous they are with the prosthetic. So that's one. They built this platform. The other thing that they did was try out methods to make the robot or the arm a little more automatic, right? Rather than just tracking the way that the muscles in the upper arm were activating in order to control the arm. That was the kind of baseline, right? They read the muscle signals and try to figure out what the arm is trying to do. They brought in where the person was looking and their body posture to take some guesses about what they're trying to do, right? Even if the arm doesn't tell the whole story, maybe the arm says, I'm trying to grab something, and the person's looking right at that red block in the top right. So then the smart arm can go grab that red block automatically. So this is earlier stage stuff, mostly computer science, mechanics, math, that could lead to better developments in actual real prosthetics and maybe speed up the development there, help some people with upper limb who use an upper limb prosthesis. Next one is on exoskeletons. So I mentioned earlier that most of the successful exoskeletons have been for people with total spinal cord injury. There's a lot more people out there with walking difficulty. There's over 200 million people around the world with some sort of walking difficulty. It could be weakness after a stroke. It could be any other lower limb disability, Parkinson's, cerebral palsy. All sorts of things cause difficulty getting around the world. What we want is an exoskeleton that doesn't just help people that have no function in the lower limbs, but that can work with a person who has some voluntary control and help them out, help them use less energy. That was historically actually really difficult because as soon as you have the person and the robot competing, for a long time, the person, in the research, all the results were saying the person still had to use more energy because they're carrying around all these motors and all these batteries, and the robot doesn't really know what they want. So it's guessing, and they're like fighting it, and it's actually hard to carry around an exoskeleton. In more recent research, they've finally gotten it to the point that they can actually save some energy by wearing an exoskeleton. So that's a big step on its own. This research saves a little bit more energy, again, using AI. So what they did was have a person wear an exoskeleton and walk this whole course. So that on the right is kind of a schematic of the walking. It's up a bunch of stairs, down a bunch of stairs, down some ramps, up some ramps. They use that as the training, right? To see how are people, not how are people walking, but how can the exoskeleton tell if somebody's walking upstairs or walking on flat ground or walking on a ramp? Because the way you walk in each of those situations is totally different, the movements that you make. And the exoskeleton needs to adapt to that if you don't want to feel like you're fighting it. So they first took all that training data, same as before, same as the other thing, right? You know what the data is, you put it into the computer, it kind of works out. These are the essential things that tell me, hey, this is stairs, this is flat ground, this is a ramp. And then when you give it a new scenario, it can identify those situations. That's exactly what they did. And they found that they were able to double the energy reduction. So with a normal exoskeleton, people were saving about 3% of their energy use. Doesn't sound like a lot. I'm sure it feels like something, right? With this, they were able to save 6% of the energy, or use 6% less energy. So positive results. Again, all of this is like fundamental research, right? This is recently published, and it will build into things and build, like on that first slide, I presented a bunch of commercial devices, right? All of that starts somewhere. This is kind of where it starts. And I think this stuff is the most exciting. Of course, I'm not an academic, so I didn't end up doing this. So moving on, it's been a little mechanics focused. It's going to get a little bit more biology, chemistry. So I'm going to talk a little bit about acute organ injury, and there's a couple research projects that have to do with this. So acute organ injury, lots of millions of people. I put that because it covers a lot. It's like a really broad category. It can be heart attack, stroke, kidney or liver failure, or failure of any other major organ. So I couldn't really find a good statistic on how many people experience it, but definitely more than tens of millions. Definitely important. What can be done? Repairing or replacing organs is one option, right? So organ transplants are something, but maybe there's stuff we can do to help the body repair itself, or just do partial replacements or replacements that don't rely on having a donor available. So the first is 3D printing heart tissue. So rather than needing a donor heart, creating heart tissue in the lab that can function as regular heart tissue. This one is really crazy to me. Like, it's wild stuff going on. That bridge between physics and chemistry and biology and mechanics is cool here. So what the first step is you want to grow heart cells, but heart cells need something to grow on. And they need something to give them structure, right? They're not going to just grow. They'll just grow as a blob in a petri dish otherwise. So what they 3D print is that structure. So it's a structure that is available and attractive to heart cells that can help them survive. So that's a big knowledge of biology, right? Of like, what do these heart cells need that they're going to survive and thrive in this little thing that was synthetic, that's not the human body? So that's step one. Step two is we need those heart cells to beat. So the way that the heart works is it's exposed to an electrical signal sent by our nervous system. The muscles contract and we get blood pumping, right? Or the muscle cells contract and we get blood pumping through the heart. So how do you get that electrical signal to this device? In like a pacemaker, they put wires in the heart. In the structure, they put solar cells, like the solar cells you might use to power your house. They have tiny little solar cells that when you shine light on them, produce an electrical signal. Solar-powered heart. Wild. So they've got this whole thing that they're printing. They grow cells on it. They shine light on it. And when they shine light on it, that electrical signal triggers and the heart cells contract. And they implanted this thing in a rat, attached just a patch of it to the rat's heart. And by pulsing light at the patch, they were able to accelerate or slow down the rat's heart rate. So this is early stage stuff, but thinking about light, right? It doesn't have to be visible light. Some light goes through our bodies. So you can have this thing implanted, shine light on it that would go through the rest of your skin, get absorbed by these little solar cells, and help your heart keep pace. You know, I don't know, 10 or 15 years down the road from the rat trials, but we'll get there. This next one is pretty much purely chemistry and biology. So this is getting organs to repair themselves, or helping organs repair themselves. So mitochondria, we've all learned about the powerhouse of the cell. It produces energy for our cells to use. And there have been there's been successful trials for organ injury of mitochondrial transplant. So injecting mitochondria at the site of an injured organ, they produce more energy and accelerate healing in that region. The problem is that mitochondria are used throughout our body. They have no way to know, oh, hey, this is an injured area, this isn't. So once you put them in, they just disperse pretty much immediately. So they help, but not for long. So this group decided, okay, what doesn't disperse? There's cells called neutrophils that are part of the inflammation process in the body. And they're attracted to those inflamed zones, those areas where there's an injury. So what they did is they put the mitochondria in a neutrophil costume. They took that outer layer of the neutrophil, wrapped it around the mitochondria, and sent it in to the injured area. So the first effect that this serves is that when you inject it, all of that inflammation around the injury gets attached to by these mitochondria with the neutrophil costume. And the mitochondria can do its work of producing energy for the cell to use and accelerating healing. The other thing that this does is reduce inflammation, because you have all these neutrophils in there binding to the inflammation signifiers, everything that's saying I'm inflamed. All the other molecules in your body, all the other cells that are actually causing that inflammation, all the immune cells that are trying to fix something, but just, making it inflamed, raising the temperature, doing all these things that don't really help healing, they don't have a place to go. They don't see it because the neutrophils are taking up all that space. So this one change serves those two purposes. This is pretty much pure biology, biochemistry. I put a little bit of math in there because there's probably some math, but not that much. This one was really cool. I don't know, they're all really cool. I don't need to say that. Let's see. I was gonna stop at 40 minutes. I'm a little bit over that. I have a couple more examples, or I could take some questions. Okay. All right, so next step, osteoporosis. Osteoporosis affects around 200 million people globally. The problem is a weakening of the bones. So it causes high risk of breaking bones, back pain, potentially stoop posture. And that risk of breaking bones is, time in the hospital potentially, can lead to, not a lot of good can come from it. So what is osteoporosis? It's just the processes in your body not being able to keep up. So your bone is a living tissue. It has cells, it has blood vessels. And throughout your life, it's rebuilding and breaking itself down. In osteoporosis, especially later in life, that building process can't keep up with the breaking down process. So this picture on the right here, you end up with your bone not having much bone left, right? It's very low density, prone to breaking. But the problem gives us a simple answer, right? If your bone growth can't keep up, just make that bone growth faster. So there's a molecule, nitric oxide, that triggers both bone growth from bone stem cells, triggers them to make more bone, and blood vessel growth. So more blood vessels to grow into the bone, provide nutrients, bring blood where it needs to go. The problem, kind of like the mitochondria, nitric oxide isn't even a cell. It's just a molecule. It's just a chemistry thing. It'll just float around wherever, go where the concentration tells it to go. So again, you need a way to target this. The other problem is that the way that bone stem cells and the cells that lead to blood vessels growing work, they're a little bit particular about where they grow. So even if you can put all these this nitric oxide in one place, you need to bring in all those cells that will work on actually rebuilding the bone. So what this group did was they made a gel. The gel mimics some of the structure of bone. It has a bunch of calcium, which attracts the bone stem cells. And when you inject that into bone, the bone stem cells are attracted, they start living on it. Those bone stem cells are gonna produce bone tissue, right? The stuff that is actually our bone, right? So all that stuff is attracted there. It starts to grow on this gel, and it starts to produce bone tissue because we've got all this nitric oxide right there, right? In the gel, held in these little capsules. It starts releasing nitric oxide right where it needs to be and getting all this new bone to grow. So this one is a lot of chemistry and biology again. This one's a little bit more mechanics too, though, because we need to think, how do you create a gel that you can inject, but that ends up looking to the cells like it's bone, right? Or like it's tissue that it likes. So you have to think about all of those properties and kind of try to mimic the biology the best you can, but with something synthetic, right? The last thing I want to talk about is pregnancy complications. In general, and there's a lot of potential complications in pregnancy. I'm going to focus on a couple. Preeclampsia, which is elevated blood pressure coupled with symptoms of organ failure, especially kidney failure. This can be really dangerous if untreated, and it's important to catch it early because something like just taking low-dose aspirin from an early time can really reduce the risk of developing this. The only cure once you develop it is to deliver the child. So a lot of times this leads to preterm birth because they intentionally deliver the child early to cure the mother. And gestational diabetes. This one is a little bit, it's as serious as diabetes is. It resolves after birth. But if untreated, it's the same as not treating diabetes, so elevated blood sugar and all of the things that come with it. Both of these, if detected early, can be managed well and pose a much lower risk. So this is another diagnostic device, similar to the Hep C one that I started with. Also using AI. So what they started with here is this knowledge that there are things called extracellular vesicles. These are little capsules of proteins and other signals, they're not cells, that float around in your bloodstream. And specifically, these are placental extracellular vesicles that are floating around in the maternal blood. So there's a blood connection there for these extracellular vesicles. So they first analyzed all of the different signals, all the different proteins in there, and found a few that were associated with, so at an early term, they took these blood samples at about, I think 30 to 120 days into the pregnancy. Usually those two conditions, preeclampsia and gestational diabetes, are diagnosed about 140 days into pregnancy. So they took these samples early, and they found a couple of signals in these extracellular vesicles that were associated with pregnancies that went on to develop these complications. So they used the AI thing for that, put in a bunch of data, they know the outcome, and then they kind of identify which of these signals are associated with the outcome. Then to develop a test, they followed a similar process, right? We have some signal that we can develop a receptor for, something that's going to grab onto that signal, capture it. They attach those little grabbers, this time to magnetic beads. I think they called them nano roses, which is nice. They kind of look like roses if you are up close. But they attach those little grabbers there. The grabbers grab onto the extracellular vesicles if they're positive for these signals that indicate gestational diabetes, preeclampsia, and hold on to them. Again, you can wash away all the rest of the junk. To wash it away, you hold a magnet next to the thing, those magnetic beads are stuck to it, and you wash away all the rest of the stuff. So you just have these magnetic beads with our extracellular vesicles present. The next step is putting that into another reaction that has more of those grabbers, that if there's extracellular vesicles, you'll get a color change. It's a visible color change. The thing is clear if there's none of the signal, blue if there is. So if you see blue, you're positive for these indicators and at a high risk of developing gestational diabetes. In this case, they found a clear link between this and gestational diabetes. So this is an early diagnosis method for gestational diabetes with promise for preeclampsia as well, but they didn't report that in their results. Let's see. And that's the tour. That's the tour of biomedical engineering. I'm happy to take any questions now. Yeah.
What company do you work for, and what do they specialize in?
I work for a company called Noah Medical. They make medical robotics specifically for